Settle in and let the room get a little quieter with every breath you take. Somewhere in the early hours, under a small circle of lamplight, a brush moves slowly across a watch dial. The paint is pale, almost ordinary, until the lights dim and the numbers begin to glow all by themselves. It looks like a tiny kindness, a soft green promise that time can be read in the dark. But in science, glow is just another word for energy leaving a place it can no longer stay. Tonight, with your sleepless scientist keeping you company, you will drift through the gentle mechanics of that light, not to frighten you, just to understand how something invisible can feel like nothing at all, until it adds up. You are sitting at the long table now, shoulders slightly forward, because the work wants you close. The room smells like varnish, damp paper, and the faint medicinal bite of solvent. A row of desk lamps makes small islands of warm light on the wood. Everything beyond those islands is dim, as if the factory is trying to keep its secrets. Your brush is thin, and your hand learns a careful rhythm. Dip, wipe, touch, pull a line that becomes a number. The dial is the size of a coin, and it demands patience like a quiet animal. Around you, other brushes whisper the same motions again and again. It is repetitive work, the kind that makes time feel smooth at the edges. And the paint is marketed as a miracle because it does something paint is not supposed to do. It shines by itself. No candle, no battery, no trick, just a soft green glow that blooms when the lights go low. If you were only a person who liked pretty things, you might call it comforting. If you were a company selling watches, you would call it modern. If you were a tired worker, you might call it a small extra joy, like finding a warm spot in winter. But the glow is not a decoration. It is a symptom. A tiny, steady confession that atoms inside the paint are rearranging themselves. Not dramatically, not with fireworks, just patiently. Every glow is a message, sent out without asking if anyone wanted to receive it. The luminous paint used here is usually a mixture. Radium salt, often radium bromide or radium chloride, is blended into a binder. Then zinc sulfide is added, and that is the part that actually glows. Radium is the rude guest who will not stop talking. Zinc sulfide is the lampshade that turns the noise into light. The radium spits out radiation, and that radiation hits the zinc sulfide crystals. The crystals respond by releasing little packets of visible greenish light, a quiet chemical conversation, translated into something the eye can understand. So when you see the numbers shining, you are watching energy falling out of atoms. You are watching a battery that cannot be switched off. And because it is always on, it feels dependable. That is how dangerous things often introduce themselves. Dependable. In these workshops, people used to call the paint undark, a sweet word like something you would dab on a child's nightlight. And there is something almost cozy about it at first. In the dim corners, the painted dials wait in trays, and each tray glows faintly, like a shallow box of captured moonlight. If you lift one dial toward your face, it looks harmless. It does not smoke. It does not sting. It does not smell different from any other paint. The glow is so gentle that your brain files it under safe. Your brain is trying to help. It is using the rules it knows. Bright fire is hot, so avoid it. Sharp thorn hurts, so avoid it. Rotting meat smells bad, so avoid it. But radiation does not cooperate with those rules. Radiation is not a smell. It is not a sound. It is not a warning color painted on nature's packaging. It is simply energy traveling through space. And sometimes through you. You can do this job for a while and believe nothing is happening at all. That belief is the first true hazard in the room. Because the glow is visible, people assume the glow is the danger. But the glow is only the polite part. The light is what's left over, the part that escaped as a soft green sigh. The real story is in what you do not see. In the alpha particles, the beta particles, and the gamma rays leaving radium as it decays. And once you've watched the paint glow so politely on the dial, it's natural to wonder what exactly that glow is made of. Radiation, at its simplest, is an exit. Energy leaving an atom because it cannot stay balanced the way it is. Some atoms are stable, and they sit quietly for longer than civilizations. Others are unstable, and they slowly, stubbornly change into something else. Radium is one of those stubborn ones. It does not explode. It does not hurry. It just keeps shedding energy, piece by piece, like a tree dropping leaves in a windless room. The strange part is how little it feels like anything. A hot stove argues with your skin immediately. A loud sound argues with your ears. But radiation can pass through you in complete silence. Your body has no built-in sense for it. No nerve ending that says, that was an alpha particle. No instinct that says, that gamma ray went straight through your chest. Perhaps we should leave. Most of the time, you feel nothing at all. That is why it is so easy to be casual around it. That is why early marketing could call it healthy, even invigorating. People once put radium into tonic waters and face creams. They treated it like bottled modernity. They did not understand the bill would arrive later. Not all radiation behaves the same way. And that is where the story becomes quietly technical. Alpha radiation is heavy and clumsy. An alpha particle is basically a helium nucleus, 2 protons and 2 neutrons bundled together. It is energetic, but it does not travel far. A sheet of paper can stop it. The outer layer of your skin can stop it. It is like a very strong person who cannot fit through a doorway. Outside the body, alpha particles are often not the main worry. Inside the body, they become brutal. Because if the alpha source is tucked into living tissue, the alpha particle dumps its energy over a very short distance. That short distance might be the width of a few cells. So the cells take the full hit. Beta radiation is lighter and more nimble. A beta particle is usually an electron, moving fast enough to be a problem. It can travel farther than an alpha particle. It can pass through paper. It can burn skin under the right conditions. It is stopped by materials like plastic, glass, or thin metal depending on its energy. Gamma radiation is different again. Gamma rays are not particles with mass, like alpha and beta. They are high energy light, and they are very good at going places you would rather they did not. They can pass through the body and through many materials unless you use dense shielding. Lead, concrete, thick steel, layers upon layers, like trying to block gossip in a small town. So the danger depends on the type of radiation and where the source is. A radium-painted dial on a table gives off radiation, but much of it is reduced by distance and by the materials around it. Put it in your pocket every day, and the exposure is closer, more personal. Touch it constantly, and it becomes familiar. Put it in your mouth, even in tiny amounts, and now you have invited it into the only place it truly thrives. The danger is not always a single moment. It is not always a dramatic accident. Often, it is time, closeness, repetition, a tiny exposure that returns every day like a quiet coworker who never takes vacation. Imagine sleeping beside a small ember that never goes out. One night, it seems harmless, even comforting. But months pass, years pass, and the ember has been warming the same spot the entire time. The heat is not loud, it is persistent. Radiation is like that, except your body cannot feel the warmth as it happens. It only notices after something has changed. And because you cannot feel it happening, the next part of the story is how people learned, slowly and painfully, what the body does with that invisible energy. In the workshop, there is a habit that looks almost tender. You want the tip of the brush to be perfect, not frayed, not splayed, perfectly pointed, like a needle made of hairs. A sharp point makes sharp numbers. Sharp numbers make good dials. Good dials make supervisors nod. And nods are a kind of currency. So you do what you were taught. You bring the brush to your lips. You roll it gently, and you pull it away with the tip refined into a point. Lip pointing, a tiny ritual, an ordinary gesture, the kind you do without thinking, because thinking would slow you down. Once, twice, 100 times in a shift, the paint has a taste, if you notice it. Chalky, metallic, something between dust and medicine. But you do not notice it for long. Your mouth becomes part of the tool set, like a rag or a cup of water. The company calls it safe. Sometimes they call it beneficial. There were years when radium carried a strange glamour, like a celebrity that could not be ignored. People associated it with discovery, with Marie Curie, with the thrill of invisible forces made visible. So when someone tells you it is fine, your brain accepts the story easily, because the glow is pretty, and pretty things are rarely accused of being murderous. This is how the radium enters you, not as a cloud, not as a spill, not as a catastrophe, but as a routine, a habit reinforced by speed and expectation. Radium in the paint is not just sitting there as a passive pigment. It is an element that is unstable, and it keeps decaying, releasing energy and transforming into other elements along the way. When you swallow tiny amounts, those atoms are now inside a wet, warm environment filled with salts and proteins. Your digestive system is not designed to recognize radium as a special threat. It recognizes minerals. It recognizes calcium, magnesium, sodium, iron. It has transporters and chemical pathways that move certain ions across membranes. Radium can slip into that world because, chemically, it resembles calcium. It belongs to the same group on the periodic table, the alkaline earth metals. That family resemblance is the key to the tragedy, because your body does not treat radium like a foreign invader at first. It treats it like a resource. And while all this is happening, the world above the workshop keeps moving in its usual way. There are newspapers and streetcars and dinners and small jokes. There are co-workers who dab a bit of glowing paint on their nails for fun. There are parties where someone smears it on their teeth, grinning in the dark like a mischievous ghost. It is not done out of malice. It is done out of trust and out of the simple human desire to play with something new. In the short term, the body is quiet about it. There is no alarm bell, no instant pain, no immediate punishment for the mistake. The delay is part of what makes it so cruel. Cause and effect are separated by enough time that people start inventing other explanations. Stress, poor diet, bad luck, anything but the glow, because the glow still seems like a kindness. But the brush tip ritual continues, and each time it is not much. Just a speck, just a dusting, just a trace. Science is often the art of understanding how traces become totals. And once the radium is inside, the real problem is that your body can't tell the difference between a useful mineral and a dangerous one. Calcium is not optional. Your nerves depend on it. Your muscles depend on it. Your bones are built with it, and your blood chemistry is constantly negotiating with it. So your body is always moving calcium around, storing it, borrowing it, putting it back. Bones are not dead stone. They feel solid and permanent, but they are living tissue. Inside them, cells are constantly working. Osteoblasts build new bone. Osteoclasts break old bone down. It is a slow remodeling, like a house that is never finished, only maintained. That means minerals are always being deposited and removed in tiny amounts. When radium is present, it can ride the same pathways. It can be incorporated into bone because the body reads it as close enough. Radium behaves like calcium in chemistry, but it behaves like radiation in physics. So once it is in the bone, it becomes a long-term tenant. And radium has a long half-life, roughly 1,600 years for radium-226. That is longer than most empires, longer than most languages remain recognizable. It means the radium in your bone is not going to politely stop because you retired. It will keep decaying quietly inside the place your body uses as a mineral bank. Now, remember alpha particles. Outside the body, they are often blocked easily. Inside the body, they deliver their energy to whatever cells are nearest. If radium is lodged in bone, that energy is delivered to bone cells and to the bone marrow nearby. Bone marrow is where blood cells are made. It is a soft factory inside the hard scaffold, a factory you never see, but you cannot live without. Radiation damage is not magical. It is physical. It happens when energetic particles or rays knock electrons out of atoms in your tissues. That process is called ionization. Ionizing radiation can break chemical bonds. It can damage proteins. Most famously, it can damage deoxyribonucleic acid, the long molecule that holds genetic instructions. Your cells do have repair systems. They find breaks and patch them. They correct mistakes. They are, in their own quiet way, diligent. But repair is not perfect. And when damage is repeated, when the same tissues are exposed again and again, the chance of a serious error rises. Some errors kill the cell. Some errors change it. and changed cells can behave badly in bone tissue. One of the slow, terrible outcomes can be bone death and cancers like osteosarcoma. In the blood-forming marrow, damage can contribute to leukemias and other disorders. The timeline can be long, and that makes it confusing. Weeks can pass with no clear sign. Months can pass with only vague aches. Then, teeth loosen. Jaw pain appears. Infections that will not heal begin to take hold. People at the time sometimes called it radium jaw, a phrase that sounds almost quaint until you understand what it cost. The body is loyal. It keeps trying to rebuild. It keeps sending resources to damaged areas. But when the blueprint is being quietly ruined, loyalty becomes a trap. Your bones keep remodeling around a source of radiation that never sleeps. And because the damage doesn't arrive all at once, the next chapter is the slow, frustrating process of proving what's happening. At first, symptoms look like the kind of thing a busy world likes to dismiss: fatigue, aches, tooth problems, anemia. And because those symptoms are common, you are offered common answers. You are told you are working too hard. You are told you are not eating enough. You are told you have an infection, or bad teeth, or nerves that need calming. You learn a strange lesson about uncertainty. When pain is vague, the world can pretend it is imaginary. And when the cause is invisible, the pretending gets even easier. You sit in a doctor's office that smells like soap and paper. You try to describe what is happening in your own words. Your jaw aches, deep and dull, like a bruise inside the bone. Your teeth feel untrustworthy. Your fatigue is not the kind that fixes itself with sleep, but a story needs a villain the listener can picture. So the early guesses drift toward things people already fear. Syphilis becomes a convenient accusation in some cases. It is a diagnosis that carries shame, and shame keeps people quiet. It is not always cruelty. Sometimes it is just ignorance wearing a white coat. Medicine, in those years, is still learning how to hear women properly. It is still learning how to connect slow harm to a slow cause. And you, the person living inside the symptoms, are asked to be patient. Patience is easier when you are not the one losing pieces of yourself. The factory keeps humming, the dials keep glowing, and the company has a story too. The story is that the paint is safe. The story is that the work is clean. The story is that the women are simply sickly. A female trouble explanation. Vague enough to be unprovable, it is a very practical kind of denial. Because if the paint is dangerous, then everything changes. The equipment changes. The process changes. The profits change, so the easiest path is to insist nothing is wrong. But bodies are stubborn witnesses. They keep testifying even when no one wants to take notes. The strange thing about radiation injury is how it can imitate ordinary illness. Infections show up because tissue is weakened and healing is impaired. Anemia appears because marrow is damaged and blood production suffers. Bone pain arrives because bone is not just a structure. It is a living negotiation. And when that negotiation is disrupted, it can become a slow collapse. If you could shrink down and walk through your own jawbone, you would hear it. Not a sound, exactly. More like a quiet crumbling. Bone is built from collagen, a tough protein scaffold mineralized with calcium phosphate. It is strong, but it is not invincible. It depends on blood flow. It depends on healthy cells. It depends on time to repair tiny microcracks. Radiation turns that repair into a gamble. Some cells die before they can do their jobs. Some cells survive with damaged instructions. And infections love damaged territory. Bacteria do not need much. They need a foothold. They need a place where the immune system is distracted. Your mouth is already full of microbes, even when you are healthy. The mouth is a warm, wet city with crowded streets. Normally, the walls hold. When tissue breaks down, the city spills outward. The jaw especially becomes a cruel stage because teeth are anchored in bone, because chewing applies force day after day, because every meal is a small stress test. So when the jawbone begins to fail, the failure is public. Teeth loosen, gums swell, abscesses form, pain becomes harder to ignore, and then sometimes something even worse happens. Pieces of bone can die, a process called osteonecrosis. Dead bone does not heal. Dead bone does not fight. Dead bone just sits there, fragile and exposed. It can fragment. It can be removed in surgery because there is nothing else to do. And in that era, surgery is not gentle. Anesthesia exists, yes, but antibiotics are not yet the reliable safety net they will become. Every procedure carries risk. Every wound is a doorway. So you begin to see why the story is slow. Not because the harm is subtle, but because the proof is hard. The radium is inside. The pain is inside. But evidence, the kind that convinces courts and companies, has to be made visible, and making the invisible visible is one of the great themes of science. It sounds noble. In practice, it is paperwork and arguments and exhausted people repeating themselves. You watch the early investigators circle the truth like tired dogs. They sniff around symptoms. They compare cases. They look for patterns. But there are distractions everywhere. Some workers smoke, and smoking harms the mouth and gums. Some workers have poor nutrition, and malnutrition weakens the body. Some workers have dental problems already, because dentistry is not a universal luxury. A company can point to any of these and shrug. A shrug is cheap. A safe workplace is not. What finally begins to bite through the fog is the sheer clustering. Too many young workers with similar, unusual injuries. Too many jawbone failures. Too many deaths too soon. Statistics, at its heart, is the science of noticing when bad luck has a pattern. And once you suspect a pattern, you need a mechanism. You need a how. In the early 1900s, radioactivity is still a relatively new language. Marie Curie and Pierre Curie have isolated radium only a couple of decades earlier. Scientists know it emits radiation. They know it can burn skin. There are early reports of radium burns, like sunburn, that arrives with a delay. They know X-rays, another form of ionizing radiation, can harm tissue with too much exposure. Some early radiologists lose fingers or develop cancers because no one warned them. So, the clues exist. They are scattered across different rooms, in different buildings, in different minds. Your job, if you are trying to prove harm, is to gather those clues and put them on one table. This is where the story turns legal and slow and very human, because a lawsuit is not a scientific paper. It is a performance of certainty. It demands names, dates, causes, effects. It demands a clean line between exposure and outcome. Biology rarely offers clean lines. Biology offers timelines with smudges. Biology offers probabilities. And yet, the women who become known as the Radium Girls in different factories and different towns keep pushing. They speak to journalists, they speak to attorneys, they undergo examinations. They allow their private suffering to become public evidence. This is not glamorous courage. It is the kind that looks like showing up again and again while feeling ill. It is insisting that your pain is not a personal failure. It is insisting that the glow meant something. In the background, companies hire experts. Experts can be honest, or they can be purchased. Sometimes they are both, depending on the question asked. The companies argue about dosage. They argue about alternative explanations. They argue about whether the paint could really do this. They argue about time, because time is useful to anyone trying to avoid responsibility. If the harm takes years, then perhaps it was something else. If the harm takes years, perhaps the victim cannot prove where it began. If the harm takes years, perhaps the victim will not live long enough to finish the case. That is not cynicism. That is just how incentives behave. One of the turning points in understanding internal radium exposure comes from a grim fact. Radium, once inside bone, stays radioactive. That means a body can remain measurably radioactive. The bones themselves become a source, not metaphorically, physically. And yes, it sounds like a ghost story, but it is simpler than that. It is atoms decaying on schedule, indifferent to the owner of the atoms. Scientists begin to look for ways to measure this. They use early radiation detectors, often electroscopes at first. An electroscope is a simple device, thin metal leaves that repel each other when charged. Ionizing radiation makes the charge leak away faster. So, if a sample is radioactive, the electroscope discharges sooner. It is not a sleek instrument. It is not a digital readout. It is a delicate, slightly fussy piece of kit that turns invisible ionization into a visible motion. And it is enough to say something is there. Later, more advanced measurements come. But in the early days, even proving presence matters. Because once you can show radium is inside the body, the argument changes. It is no longer just workers feel sick. It becomes workers contain the source of injury. That is a harder thing to wave away. The science of dose, too, begins to mature. Dose is not just, was there radiation? Dose is how much energy is deposited in tissue over time in a specific place. A brief exposure to a high dose can burn. A low dose over long periods can quietly raise cancer risk. And internal exposure is different from external. If you carry radium in bone, the distance between source and tissue is nearly zero. No shielding, no stepping back, no quitting the job and leaving it behind. The source goes home with you, embedded in the skeleton. There is an old, dark joke in radiation safety. Distance is your friend. Time is your enemy. Shielding is your compromise. Internal contamination makes distance irrelevant. It makes shielding a fantasy. It leaves time, and time always gets paid. The legal system, of course, is not built to move faster than time. It moves at its own pace, a pace that favors whoever can afford to wait. But the cases do create pressure. They create headlines. They create public discomfort. And public discomfort is one of the few forces that can make industry change its habits. In some factories, practices begin to shift. Workers are told to stop lip pointing. They are given better ventilation. They are offered protective gear sometimes, not always out of compassion. Sometimes simply because it is cheaper than losing in court. Safety, in the modern world, is often built from the rubble of lawsuits. It is not poetic, it is functional. And functional is better than nothing. The tragedy is that by the time the broader truth becomes accepted, many workers have already been harmed. Radiation injuries do not rewind when a policy changes. Cancer does not apologize when a memo is issued. Bone does not regrow simply because management has been educated. This is the part of the story that teaches you what science really is. Science is not just curiosity. It is the slow replacement of comfortable stories with uncomfortable mechanisms. It is the insistence that if something happens repeatedly, it has a cause worth naming. And that insistence, in the radium dial painter story, is paid for in bodies. If you want a clearer picture of what was happening, imagine the scale. An alpha particle travels only a tiny distance in tissue, often described in micrometers. That is, millionths of a meter, a scale smaller than dust. So the damage is intensely local, like a tiny shotgun blast delivered to a few cells at a time, but delivered again and again and again from a source that never sleeps. Cells near the radium deposits take repeated hits. DNA breaks occur. Repair enzymes rush in. Sometimes they fix it. Sometimes they miss a stitch. And when the stitch is missed in the wrong gene, in the wrong cell, at the wrong time, the cell can become something dangerous. Cancer is not one thing. It is many diseases, all united by a theme. Cells stop obeying the rules of the body. They divide when they should not. They refuse to die when they should. They recruit blood vessels. They invade space. They are not moral failures. They are biological rule breaking, encouraged by damage and chance. Radiation can increase the odds of that rule breaking. It does not guarantee it. It just loads the dice. And loaded dice feel like fate when they land badly. In the radium cases, the jaw and bones are common sites, because that is where radium settles. But radiation can also affect the blood system. Bone marrow is sensitive. It makes rapidly dividing cells, and rapidly dividing cells are more vulnerable to DNA damage. So disorders like aplastic anemia, where marrow stops producing enough blood cells, can appear. Leukemias can develop. These outcomes were not fully understood at first. They become clearer over decades as more cases accumulate and better science is built. That is another slow truth. The full consequences of exposure can take a lifetime to map. And the radium story becomes a cornerstone in occupational health, not because anyone wanted it to be. Because the evidence was written in human tissue and it could not be completely erased. If you zoom out past the courtroom and the clinic, you can see the larger pattern. Industrialization creates new materials, new processes, new jobs. It also creates new exposures, dusts and fumes, solvents and dyes, metals and radiation. And at first, the benefits arrive immediately. The costs arrive later. The benefits are a paycheck, a product, a glowing dial you can sell. The costs are a slow sickness that does not have a simple label yet. This time lag is the most dangerous feature of many hazards. Your brain is not built for delayed punishment. It is built for immediate feedback. Touch fire, feel pain, learn quickly. Swallow tiny specks of radium. Feel nothing. Repeat for months. The learning does not arrive until the body is already paying. And the world, being a world, prefers not to learn if it can avoid it. So the people most affected are often the ones with the least power to refuse. Workers, children, communities near factories, anyone who cannot simply step away. The radium dial painters become a symbol, but they are not unique. They are one chapter in a thick book of "we did not know," followed by "we did not want to know," followed by "now we have to know." And once the truth begins to settle in, you start seeing the same pattern elsewhere. Other beautiful inventions with hidden costs. In another room, in another decade, you are painting a wall. The paint is bright, smooth, and satisfying. It covers in one coat. It dries into a tough skin that resists weather and time. It has a sweetness to it, a clean look, a sense of permanence. That paint may contain lead. Lead makes paint durable and flexible. It helps pigments keep their color. It helps the coating resist moisture. From a purely practical viewpoint, lead paint is excellent. From a biological viewpoint, it is an uninvited experiment on the nervous system. Lead is a heavy metal that interferes with enzymes in cell signaling. It can mimic calcium in certain contexts, slipping into places calcium belongs. It can disrupt neurotransmitter release. It can impair brain development, especially in children. Children are not just small adults. Their brains are building connections at a furious pace. So a toxin that disrupts that building can have lifelong effects. Reduced attention, learning difficulties, behavior changes. Not always dramatic in one child. Sometimes it is subtle. Spread across a population, a small shift in average performance can mean a lot. When multiplied by millions, lead also harms adults. It can raise blood pressure. It can damage kidneys. It can affect fertility. But the cruelest part is how it can hide in old housing. Paint flakes become dust. Dust settles on floors and windowsills. Small hands touch the dust. Small hands go into mouths. And the hazard is not the bright painted wall you admire. It is the invisible grit you inhale and ingest. Again, you see the theme. The danger is not always in what you can see. Sometimes it is in what crumbles. In another building, perhaps a shipyard or a construction site, the hazard is praised for the opposite reason, not for brightness, for invisibility, for being woven into walls and pipes where you never have to think about it. Asbestos is a family of minerals with thin, strong fibers. It resists heat. It resists fire. It insulates. It is, from an engineer's viewpoint, almost magical. So it ends up in insulation, tiles, brake pads, and countless products. As long as the fibers stay locked in place, it may seem harmless. But when asbestos is disturbed, it releases tiny fibers into the air. You inhale them. They travel deep into the lungs. The body tries to clear them, but the fibers are stubborn. They can lodge in tissue for years. The immune system responds with inflammation. Over time, the irritation can scar the lungs, a condition called asbestosis, and the risk of cancers increases, including mesothelioma, a cancer of the lining around the lungs. Mesothelioma is rare without asbestos exposure. That connection becomes one of the most damning signatures in occupational medicine. But it takes time to accept, because once again, the benefits are immediate. Fireproofing saves buildings. Insulation saves energy. Asbestos makes materials cheaper and safer in one way, while making them deadly in another. The body does not care how useful something is to industry. The body responds to physics and chemistry, not marketing. Then, there is mercury, a metal that is liquid at room temperature, shimmering like a small captured mirror. It is beautiful in the way a knife is beautiful. Mercury has been used in thermometers and barometers, in switches, in mining, in industrial processes. It binds with other metals, forming amalgams. It can be part of gold extraction. It can be part of chemical manufacturing. Mercury is also a neurotoxin. Different forms of mercury behave differently. Elemental mercury, the shiny liquid, is not absorbed well if swallowed, but its vapor is dangerous when inhaled. Inorganic mercury salts can damage kidneys and other organs. Organic forms like methylmercury can build up in food webs. Methylmercury is made by microbes in water and sediments. Small organisms accumulate it. Small fish eat those organisms. Big fish eat small fish, and the mercury concentrates as it moves up the chain, a process called biomagnification. So a person eating large predatory fish can receive a dose that did not originate in the fish itself. It originated in industrial pollution, carried by air and water, transformed by biology, and returned in dinner. Again, the pattern. The hazard moves quietly. It does not announce itself. It takes the routes the world already uses: air currents, waterways, supply chains, work shifts. None of these hazards were always used out of malice. That is one of the most uncomfortable truths. Often, they were used out of eagerness, out of incomplete understanding, out of the human habit of solving the problem in front of you and postponing the rest. Radium made dials readable at night. Lead made paint tough. Asbestos slowed fire. Mercury made measurement easy. Each one offered a clean, simple benefit. Each one carried a biological cost that was not immediately obvious. So when you live in the modern world, surrounded by warnings and labels and regulations, it can feel like overkill. It can feel like bureaucracy for its own sake. But most safety rules are fossils of old pain. They are memorials written as policies. They are the price paid for learning after the fact. And since so much danger comes from things you cannot see, it becomes oddly comforting that humans eventually learned how to measure the invisible. Imagine a small device in your hand. It is not pretty. It is a practical box, sometimes metal, sometimes plastic. It has a speaker that can click. It has a needle that can twitch. It has a simple job to translate radiation into something your senses can notice. The Geiger counter is one of the most famous of these translators. Inside is a tube filled with gas, with a high voltage applied between a central wire and the tube wall. When ionizing radiation passes through, it knocks electrons loose in the gas. Those electrons accelerate in the electric field and trigger an avalanche of ionization. That avalanche becomes an electrical pulse, and the device turns that pulse into a click. So the invisible becomes audible. A quiet danger becomes a small sound you can count. Click, click, click. It is not measuring your fear. It is measuring ionization events. It is not perfect. A Geiger counter is good at telling you that radiation exists and that it is nearby. It is not good at telling you what kind or how dangerous it is for your specific body. Those clicks are like hearing footsteps in a hallway. You know someone is there. You do not yet know if it is your friend or the landlord or a problem. If you want more detail, you start choosing the right interpreter for the right invisible language. Some detectors are tuned for alpha particles because alphas do not travel far in air. To detect them, you often need the window of the detector to be very thin. You need the source close, almost uncomfortably close, because alpha radiation is shy in open space but vicious up close. Beta particles are easier to catch because they travel farther. A detector can see them through a thin metal or plastic window, depending on the design. Gamma rays are the indifferent tourists. They pass through more things, and you need dense shielding and careful geometry. A common trick is to use a scintillator, a material that flashes when radiation hits it. The flash is tiny, but a photomultiplier tube can amplify it. A whisper of light becomes a measurable pulse. So you end up with the same theme, again and again. You take something you cannot sense and you translate it into something you can. A flash, a pulse, a click, a number on a dial. And if you are a worker or a researcher or someone unlucky enough to be near an accident, the number matters. Because radiation risk is not only about type, it is about dose. Dose is the slow arithmetic of energy deposited in tissue. Not energy passing by, but energy stopping inside you. That is why internal contamination changes everything. Inside the body, the radiation source is pressed against living cells at all times. You do not get to step away from it. You do not get to put lead walls between you and your own skeleton. So safety culture had to become a culture. Not a poster on the wall, but habits that stick. Time, distance, shielding, containment. Those are the basic spells. They are not poetic, but they work. Time means you limit how long you are near a source. Distance means you do not hug the danger, even if it is small. Shielding means you choose the right material for the right radiation. Containment means you never give the hazard a path into your lungs or mouth. In the radium dial shops, the most effective safety improvement was also the most boring. Stop putting the brush in your mouth. Provide a way to point the brush without lips. Ventilate dust. Keep paint wet so particles do not drift. Wash hands. Ban eating at the bench. It is not dramatic science. It is the kind of science that sounds like a nagging parent, and it exists because somebody, somewhere, learned the hard way that bodies are not as forgiving as schedules. The next quiet step is personal monitoring, the small diary you wear. A dosimeter is a record keeper. It is not there to save you in the moment. It is there to notice the accumulation you cannot feel. Early dosimeters could be film badges, a little piece of photographic film carried on a worker's clothing. Radiation fogs film the way light does because both are forms of energy that can affect chemistry. After a shift, the badge is developed and compared to a standard. The darkness of the film becomes an estimate of exposure. It is simple and a little crude, but it is honest. Modern dosimeters might use thermoluminescent crystals. Radiation traps energy in the crystal structure. Later, in a lab, the crystal is heated. As it warms, it releases that trapped energy as light. The amount of light tells you something about the dose. So the crystal becomes a pocket memory. It remembers what your nerves could not. There are also electronic dosimeters that give real-time readings. They can beep if rates are high. They can log exposure by the minute. They are the boring guardian angel of industrial work. Not sentimental, just persistent. All of this measuring did something important to the human mind. It took radiation out of superstition. Before detectors, radiation was a rumor. After detectors, radiation became a quantity. And once something is a quantity, you can manage it. You can set limits. You can compare risks. You can design procedures that keep people below thresholds. You can build policies that are at least tethered to reality. That is the calm power of measurement. It does not erase danger, but it makes danger less sneaky. Still, the story of radiation is not only a story of harm. That is the strange part. The same physics that damaged bone can also be aimed, controlled, and made useful. Not because the universe suddenly developed compassion, because humans became better at boundaries. And in medicine, boundaries are everything. You are lying on a table now, in a room that smells like disinfectant and warm electronics. The lighting is soft, almost kind. A machine hums nearby, patient and expensive. You are not here for a glowing watch dial. You are here because someone wants to see inside you without opening you. Radiation, when respected, becomes a kind of flashlight for flesh. One of the simplest examples is the X-ray image. X-rays are high-energy light, similar in spirit to gamma rays, though produced differently. They pass through your body unevenly. Soft tissue lets more through. Bone blocks more because it is denser and has elements that absorb X-rays more strongly. So, on the detector, bone appears bright and lungs appear darker. It is a shadow picture made from physics, a clean, quiet map of what you cannot see with your eyes. The dose for a medical X-ray is kept as low as reasonably possible. That phrase, as low as reasonably possible, becomes a kind of medical prayer, not because low is always safe, but because unnecessary exposure is just wasted risk. You also have computed tomography, often called a CT scan. Instead of one shadow image, the machine rotates, taking many X-ray measurements from different angles. A computer reconstructs these into cross-sectional slices. It is like looking at a loaf of bread, one slice at a time, except the loaf is you. The images can show bleeding, tumors, fractures, blocked vessels. The scan can be life-saving because it trades a small, controlled risk for a large diagnostic benefit. Then there is nuclear medicine, where the radiation source is intentionally put inside the body, but in carefully chosen forms. You swallow or receive an injection of a radiotracer. A radiotracer is a molecule designed to go where doctors want to look. It might concentrate in bone, or thyroid, or heart muscle. The radioactive part emits gamma rays that can escape the body and be detected. So the scanner does not shine radiation at you. It listens to radiation leaving you. You become the beacon, briefly. A very monitored beacon. Positron emission tomography, often called a PET scan, uses a tracer that emits positrons. A positron is the antimatter partner of an electron. When a positron meets an electron, they annihilate. They turn their mass into energy, producing two gamma photons, flying in opposite directions. The scanner detects those paired photons and reconstructs where they came from. So the machine builds an image of metabolism, of tissue activity, not just anatomy. Cancer cells often have higher metabolic activity and can stand out. It is not magic. It is a controlled set of tiny annihilations happening inside you for your benefit. Congratulations! You are briefly a physics experiment that someone actually planned responsibly. Treatment is the more intense side of this. Radiation therapy uses high-energy beams to damage the DNA of cancer cells. The goal is cruel in a precise way. Hit the tumor harder than you hit the surrounding healthy tissue. Because cancer cells often have weaker repair mechanisms or are dividing quickly, they can be more vulnerable. But the margin is never infinite. Healthy tissue can be harmed too, which is why planning matters. A radiation oncology team will map the tumor with imaging. They will choose beam angles like a careful carpenter choosing cuts. They will shape the beam with collimators, blocks, and multi-leaf devices. They will calculate dose distributions so the highest dose conforms to the tumor volume. They will fractionate the dose, dividing it into multiple sessions. This gives normal tissue time to repair between treatments. It is not gentle, but it is disciplined. Brachytherapy is another approach. Instead of beaming radiation from outside, doctors place a source close to or inside the tumor. This uses geometry as a weapon. Radiation intensity drops quickly with distance, following the inverse square law. So if the source is right next to the target, nearby tissue receives far less. Distance becomes your friend again, but now it is measured in centimeters. In all of these medical uses, the difference from the radium dial story is not that radiation became kinder. It is that humans became less casual. They began to treat dose like a budget. They began to treat exposure like a debt that accrues interest. They began to design systems where the numbers are known, recorded, and kept within limits. And that is the core lesson the radium era carved into policy. Invisible forces require visible accounting. If you cannot sense it, you must measure it. If you cannot measure it, you should not pretend you control it. This is why hospitals have shielding in walls, why radiology rooms have warning lights, why staff wear badges, why there are protocols, checklists, timeouts, verification steps, because the universe does not care if you meant well. The universe only cares about where the energy went. Now, when you zoom out far enough, the glow of radium starts to look less unique, because glow is everywhere. Glow is just the universe spending itself in public. In the radium paint, the glow is zinc sulfide taking a hit and responding with light. In a candle flame, the glow is hot soot and excited molecules dropping back down in energy. In a firefly, the glow is a chemical reaction, luciferin meeting oxygen, with an enzyme guiding the dance. In a star, the glow is fusion, light struggling out from a dense interior, taking ages to reach the surface. Different mechanisms, same theme. Something has energy, and it cannot keep it forever. So it leaks, it radiates, it shines. Even you glow, technically. Your body emits infrared light, a soft heat glow, because you are warm. If you sat in a perfectly dark room with an infrared camera, you would look like a ghost of heat. That glow is harmless because it is low energy. It does not ionize. It does not break chemical bonds. It just drifts away, a quiet payment to the environment. Ionizing radiation is different because its photons or particles carry enough energy per interaction to knock electrons free. That threshold matters. It is the difference between a gentle tap and a chipped tooth. The electromagnetic spectrum is vast. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. The names sound tidy, but the underlying reality is a sliding scale of wavelength and energy. Visible light is the narrow strip your eyes evolved to appreciate, mostly because the sun is generous in that range. Ultraviolet carries more energy and can damage skin, which is why sunburn exists. X-rays and gamma rays carry enough to ionize deeply, which is why they require respect. But even within a category, energy can vary. Not all X-rays are equal. Not all gamma rays are equal. Nature does not package danger in neat labels for our convenience. So the safe handling of radiation is a story of details. Details about energy. Details about time. Details about pathways into the body. Details about shielding materials and thickness. Lead is common as shielding because it is dense, with lots of electrons to interact with photons. Concrete is also used because you can build walls from it, and it works well for gamma and neutron shielding in reactors. Water is useful too, especially for slowing neutrons. Neutrons are a different kind of hazard, more common in nuclear reactors and some specialized sources. They are uncharged, so they penetrate differently. They can make other materials radioactive through activation, which is a whole additional inconvenience. But in the dial painter story, the big villain is not neutrons. It is alpha radiation delivered from inside bone. And that detail matters because it shows how context changes everything. The same radium source on a shelf is one kind of risk. The same radium source in a mouth is a different kind. This is why radiation safety people sound so picky. They are not picky because they love rules. They are picky because the universe is picky. It punishes sloppy geometry. It punishes forgotten contamination. It punishes wishful thinking. And you can see the same logic in how we handle other toxins too. Lead paint is dangerous when it becomes dust, and dust becomes breath and swallow. Asbestos is dangerous when fibers become airborne and reach deep lungs. Mercury is dangerous when it becomes vapor, or when microbes turn it into methylmercury and it climbs food webs. In each case, the key is exposure pathway, not just what something is, but how it reaches you. So modern safety is often about blocking pathways. Keep dust contained, keep ventilation working, keep surfaces clean, keep hands washed, keep food away from work areas, wear proper respirators, not a brave smile, use fume hoods, label containers, track waste. These are unromantic actions, but they are how you avoid being a case study. And case studies are exhausting because they have endings you do not want. There is another detail in the radium story that lingers, a detail that feels almost supernatural until you remember it is chemistry. Radium decays into radon gas as part of its decay chain. Radon is a noble gas, meaning it does not react much. It can seep out of materials and drift into air. In dial painting workshops, radon could accumulate in poorly ventilated areas. In homes, radon can seep from certain rocks and soils into basements. You cannot see it, you cannot smell it, but you can measure it and you can ventilate it away. Radon is a major source of natural radiation exposure for many people, especially in regions with uranium-rich geology. It is one of those reminders that you live in a radioactive universe, even if you do not work with glowing paint. The Earth contains uranium and thorium, and their decay chains produce radium and radon and other daughters. Potassium-40 exists in bananas and in you, a naturally occurring radioactive isotope. Carbon-14 exists in living things, made in the upper atmosphere by cosmic rays. The background radiation is always there, a soft static. Most of the time, it is low enough that your body's repair systems handle it as part of life. But the radium story is what happens when the static becomes a signal, localized and intense in bone. It is what happens when the universe's quiet processes are concentrated into a job, into a habit, into a mouth. If you want the darkest humor, it is that the dial painters were hired to make time visible at night. And the thing that hurt them was time itself. Not the clock time, but biological time. The slow accumulation, the delayed consequence, the long half-life, outliving the person who carried it. That is why this story shows up again and again in safety training. It is not just tragedy, it is an origin story for rules that now protect other workers, rules about radioactive materials, rules about training, rules about monitoring, rules about informed consent in the broad cultural sense. And if you have ever been annoyed by a warning label, you can trace that annoyance back through decades. Back through lawsuits, yes, but also through bodies that proved what paper would not believe. Now, since you cannot really do radiation as a bedtime story forever without making people stare at their smoke detectors suspiciously, it helps to widen the lens. Because the radium glow was a small light in a universe full of lights that also come with terms and conditions. Everything that shines is paying for it. Stars shine by burning through fuel, and when the fuel arrangement changes, the star changes. Some swell into red giants, swallowing inner planets if they happen to be in the way. Some collapse into white dwarfs, dense cores cooling over eons. Some explode as supernovae, scattering heavy elements, which is beautiful in the way a demolition is beautiful. The elements in your bones, including calcium, were forged in stellar interiors and explosions. The universe built you out of ancient violence, then asked you to be polite about it. Even the radium itself comes from uranium decay, part of a long chain that began when the Earth formed. The rock held it for ages. Then humans dug it up, refined it, and painted it onto timepieces. A geological story turned into an industrial one. The universe is like that. It will happily let you connect distant scales from deep time to a brush tip, but it will not protect you from the consequences of that connection. Speaking of consequences hiding in ordinary materials, you can look around a modern room and find quiet science everywhere. The lithium in your devices, useful, reactive, occasionally dramatic. The plastics, stable until heat and sunlight and time begin to break them down. The flame retardants, helpful in fires, complicated in bodies. The cleaning agents under the sink, perfectly normal until mixed incorrectly. None of this is meant to make you paranoid. Paranoia is a waste of energy, and you have limited supplies. The point is softer. You live in a world made of chemistry and physics, and comfort is often just well-managed hazard. A warm blanket is controlled insulation. A heater is controlled combustion or controlled electricity. A fridge is controlled heat flow. Even sleep is controlled vulnerability. You are unconscious for hours, and the only reason that works is because you built a safe enough nest. The radium dial painters were also trying to build a nest. They were earning money, they were doing skilled work, they were participating in modernity. They were not volunteering to be irradiated. And that is the part that still stings, even now. Not that nature can hurt you. Nature always can. But that human systems can translate nature into harm, quietly, while insisting it is fine. That is why measurement matters. That is why transparency matters. That is why the boring details, the dosimeters and ventilation hoods and hygiene rules are worth the trouble. Because the universe will always be indifferent. So the only kindness available is the kind you build for each other, in procedures. So when you hear the word safety, you can picture something small and dull. A checklist, a locked cabinet, a label that refuses to be poetic. Those things exist because invisible forces are excellent at exploiting human laziness. You cannot negotiate with an alpha particle. You cannot bargain with lead dust. You cannot charm asbestos fibers into leaving your lungs. So you build habits instead. And if you are lucky, you inherit those habits from someone else's bad century. Now, while you are still sitting with a radium story in your hands, there is one last, strangely soothing detail. Radium does not glow because it wants to. Radium glows because it is failing, steadily, atom by atom. It is a kind of slow surrender. And surrender is common in the universe. Everything stable eventually meets a condition that is not. A metal rusts, a battery drains, a star runs out of easy fuel. Even a body, even your body, is a long negotiation with decay. Speaking of negotiations with decay, the modern world is full of materials that behave beautifully until they do not. And we keep making the same mistake. We fall in love with the first job a material does, and we forget it has a second job too. Lead makes paint smooth and durable, and then quietly steals attention from a developing brain. Asbestos makes buildings harder to burn, and then turns into needles you can inhale. Mercury makes instruments precise, and then becomes a traveler through oceans and nervous systems. The universe does not label these as good or evil. It labels them as properties, and properties have consequences. But you are not helpless against consequences. Not anymore, because the truly comforting invention is not a new miracle material. It is the ability to notice, to detect what your senses cannot, to build instruments that act like extra organs, bolted onto the species. A Geiger counter is one of those organs. It hears ionization. A dosimeter is another. It remembers exposure. But measurement goes beyond radiation. In a quiet way, modern life is a forest of detectors. Carbon monoxide alarms sniff for a gas you cannot see and cannot trust. Smoke detectors watch for particles and for heat. Water testing kits check for lead and bacteria and chlorine levels, translating chemistry into color. Air quality sensors count tiny bits of dust you would otherwise swallow without a thought. Even a pregnancy test is a detector calmly reacting to a hormone and telling you a truth. Detection is how the human animal compensates for being made of soft tissue in a hard universe. And once you can detect, you can build culture. Culture is what happens when information becomes habit. A radiation badge is information that became policy. A fume hood is chemistry that became architecture. A respirator is particle physics turned into wearable inconvenience. And yes, it is inconvenient. Convenience is the bait. Safety is the leash. So, you can treat these rules as boring. That is fine. Boring is the goal. Boring is what you want from a workplace, from a home, from a medicine cabinet. You want hazards to be dull, predictable, and contained. You want the story to end before it becomes a chapter in occupational health. In the decades after the radium dial painters, the science of radiation protection hardened into something closer to a discipline. People stopped asking, "Is radiation dangerous?" and started asking, "How dangerous? In what form? And at what dose?" And then the next layer arrived. Not just dose, but which tissue. Not just which tissue, but which kind of radiation. Because biology is not uniformly fragile. Different parts of you react differently. Your skin can tolerate some insults that bone marrow cannot. Your lungs are vulnerable in ways your muscles are not. Your eyes have delicate tissues that dislike certain exposures. So the idea of weighting exposure by biological effect becomes important. Radiation dose can be measured as energy deposited per mass, but the biological effect depends on more than energy. Alpha radiation, for example, delivers energy densely in short tracks. It is like using a hammer instead of a gentle push. So the same deposited energy can cause more damage depending on the radiation type. This is why safety people talk about equivalent dose and effective dose. It is a way of admitting that bodies are complicated. It is a way of turning complicated harm into manageable numbers. Not perfect numbers, but better than guessing. And that gets you to one of the softer, stranger comforts of science. A lot of modern safety is built on humility, not on certainty. Humility is the admission that your intuition is not a detector, that your eyes are not a dosimeter, that your confidence does not stop an electron. So you treat the invisible with procedures, and you learn to respect what you cannot feel. This is the part where the story could stay in radiation forever. It could wander into nuclear reactors, into medical accelerators, into fallout and geology and cosmic rays. But for tonight, it helps to keep the scale human, to keep it close to ordinary rooms, ordinary objects. Because the theme is not radium specifically. The theme is the gap between appearance and reality. And that gap shows up everywhere. So let us walk into another ordinary room. You are standing in a hallway of an old apartment building. The air smells faintly like dust and detergent. The paint on the windowsill looks thick, layered, with too many generations of beige. When the sun hits it, you can see tiny cracks like dry riverbeds. You think the danger would be a sharp flake. You think you would notice the moment you touch the wrong thing. But the danger is quieter. It is the powder you cannot see, ground down over years by opening and closing windows. Lead paint does not have to peel dramatically to be dangerous. It can simply abrade, and when it abrades, it becomes dust. Dust is the perfect delivery system. It rides air currents. It settles on toys. It hides on fingertips. It becomes part of the ordinary. Lead, as a chemical element, is soft and heavy. It has a talent for fitting into biological machinery where it does not belong. It can mimic calcium, and that lets it interfere with the nervous system. Neurons communicate by releasing neurotransmitters, and calcium is part of that release machinery. So lead can disrupt signaling, like slipping wrong keys into delicate locks. In children, this matters more because their brains are in a construction phase. Connections are forming. Pruning is happening. Myelin is being laid down. The brain is basically a city building its roads while the traffic is already driving. And lead is the kind of contaminant that shows up and quietly moves the street signs. Not enough to make a dramatic collapse in one day, enough to shift outcomes over years. That is the tragedy of many toxins. They do not always produce a single cinematic symptom. They produce population-level harm. A few points off average cognitive performance, a subtle rise in impulsivity, a small increase in learning difficulties, a shift you do not notice in one child, but you notice in a community. And because it is subtle, it is easier to deny. Subtle harm is easy to ignore, especially when the people harmed are small and cannot argue in court. Lead also stores in bone, like radium in a different costume. Bone is a vault. It holds minerals, and when the body mobilizes calcium, during pregnancy, during illness, during aging, lead can be mobilized too. So old exposure can become new exposure. The past can leak into the present, chemically. This is why lead abatement is treated with such seriousness. You do not sand it casually. You do not scrape it into a cloud. You contain it. You wet it. You remove it with procedures that look almost obsessive because you are not fighting paint. You are fighting a distribution method, and the main lesson is still the same. The hazard is not the bright surface. The hazard is what becomes airborne. Speaking of airborne, there is a material that was once praised precisely because it could be turned into airy fluff: asbestos. The word sounds like something ancient and harmless, like a rock you might find on a beach. And it is a rock, technically, a family of silicate minerals. But the important feature is not that it is a mineral. The important feature is the fibers. Asbestos can be pulled into thin strands, strong and resistant to heat. That made it useful for insulation, brake pads, boiler coverings, ceiling tiles, and so many hidden places. And hidden places are where hazards go to wait. As long as asbestos is sealed, it often sits quietly. But buildings age, repairs happen, renovations happen, a pipe gets replaced, a ceiling tile cracks, a wall gets opened, and now those fibers are free. They are small enough to float, small enough to be inhaled, small enough to reach deep into the lungs, into the alveoli, the tiny sacs where oxygen enters blood. Your lungs are delicate, thin, designed for exchange. They are not designed for splinters. When asbestos fibers lodge there, the body reacts like it does to many foreign materials. It sends immune cells. Macrophages try to engulf the fibers, but fibers are long and stubborn. Some cannot be fully swallowed by a cell, so the immune response persists. Inflammation becomes chronic. Scar tissue forms. This scarring is called fibrosis. If enough scarring accumulates, the lungs become stiff. Breathing becomes work. Oxygen exchange becomes less efficient. That is asbestosis. Then there is cancer. Mesothelioma is the one people remember because it is so strongly tied to asbestos exposure. It affects the mesothelium, the thin lining around the lungs, and other organs. The latency is cruel. Decades can pass between exposure and disease, so the exposure can happen in youth and the diagnosis arrives in retirement. Time again. Time is always part of the bill, and this is why asbestos is handled with such ritual now. Negative pressure tents, special filters, protective suits, careful bagging, because if the fibers become dust, the building becomes a lung problem, and the lungs are not easily repaired. Speaking of things you cannot easily repair, mercury. Mercury is a metal that looks like a liquid secret. If you have ever seen a broken old thermometer spill, you remember the beads. They roll and split and rejoin, as if they have their own intentions. It feels alive. It is not alive. It is just surface tension and density doing what physics does. Mercury hazards depend on the form. Elemental mercury is most dangerous as vapor. In a warm room, mercury slowly evaporates. You cannot smell it. You inhale it. It crosses into blood through the lungs, and then it can reach the brain. Mercury likes to bind to sulfur groups in proteins. Proteins are the machinery of your cells. So mercury's habit of binding can jam machines. Symptoms can include tremors, mood changes, cognitive issues. Historically, hat makers used mercury compounds to process felt, leading to the phrase, mad as a hatter. Not a metaphor, a workplace exposure pattern. Then there is methylmercury, the ecological version. Microbes in water convert mercury into methylmercury. It enters small organisms, then fish, then bigger fish. It concentrates as you go up the food chain. This is biomagnification. So a distant industrial release becomes a dinner exposure. Not dramatic, not immediate, just quietly present in the muscles of a large predatory fish. This is why advisories exist for certain fish, especially for pregnant people. Developing nervous systems are sensitive. The fetus is building that same fragile wiring, and methylmercury can interfere with it. Again, the universe does not care if the mercury was useful in an instrument. It cares where the mercury ends up. Now, you might notice something these stories share. They are all about invisible travel, dust, fibers, vapors, ions, particles that drift through air and into bodies. So if you want a simple, almost boring principle of safety, it is this. If a hazard can become airborne, treat it like it wants to be inside you, because air is the easiest highway. You breathe all the time. You cannot stop. You can only filter, ventilate, contain, and monitor. And this is where detection becomes comforting again, because detection is how you keep the highway patrolled. For lead, you can test paint and dust. For asbestos, you can sample air and materials. For mercury, you can measure vapor levels. For radiation, you can count clicks and track doses. For radon, you can put a detector in a basement and let it sit, quietly accumulating evidence. Radon is worth lingering on because it is the perfect example of an ordinary danger hiding in geology. Radon is a noble gas, so it does not react much. It is produced by the decay of radium, which comes from uranium in rock. Radon can seep through soil and cracks in foundations. It can accumulate in poorly ventilated spaces. Basements are classic traps. It is invisible, odorless, tasteless. The only way to know is to measure it. Radon decays into solid daughters that can stick to dust and be inhaled. In the lungs, those decay products can emit alpha radiation. Again, alpha. Again, close-range damage. This is one of the reasons radon exposure increases lung cancer risk, especially for smokers, because smoke already damages lung tissue, and the combination multiplies risk. So here is the quiet comfort. You can test your home. You can ventilate. You can install mitigation systems that pull radon from beneath a foundation and vent it outside. A simple fan and piping. Not glamorous, but it changes your long-term exposure. And that is what modern life really is. A collection of small engineering tricks that keep your biology from being overwhelmed by physics. Now, after all these hazards, it might sound as if science is just a catalog of ways to die. It is, partially. But the other side is that science is also a catalog of ways to not die. Not perfectly, not forever, but longer, and with fewer unnecessary injuries. And that takes us back to radiation, not as harm, but as controlled help. Because once you learn to measure and limit exposure, you can start using radiation like a tool. And tools are always about boundaries. A knife is a tool if you hold it correctly. A knife is also a way to bleed. Radiation is the same kind of object, except you cannot see the blade. In medicine, controlled radiation is used to look inside you and sometimes to treat you. The reason it works at all is because biology is consistent. X-rays interact with tissue in predictable ways. Gamma rays can be detected and traced back to their source. Radio tracers go where chemistry guides them. So a doctor can turn physics into an image, and an image can become a decision. But none of that happens casually anymore. There are protocols. There are dose limits. There are people whose entire job is to calculate, verify, and double-check. Medical physicists, radiation safety officers, technologists who follow procedures with a kind of practiced boredom. Because boredom, again, is the goal. You want the scan to be routine. You want the beam to hit exactly where planned. You want no surprises. In radiation therapy, the planning can be almost obsessive. The tumor is outlined on imaging. Nearby organs are outlined too. The spinal cord, the lungs, the salivary glands, the heart, the bowel, each has a tolerance, each has a risk curve. So the plan becomes a compromise, sculpting dose in 3 dimensions. Beams come from multiple angles. They overlap in the tumor like converging flashlights. Outside the target, each beam is weaker, spreading the dose. Inside the target, the overlap creates intensity. This is not kindness. It is geometry used for survival, and there is an additional layer of realism. Patients are not statues. They breathe. Organs move. Tumors can shift with respiration. So, modern techniques sometimes track motion or gate the beam to breathing cycles. Sometimes imaging is done right before treatment to verify position, because a few millimeters matter. A few millimeters is the difference between tumor and spinal cord. Congratulations, you are made of soft parts that drift. So medicine adapts. There are also internal radiation treatments. Iodine-131 is used for certain thyroid conditions. because the thyroid naturally concentrates iodine. So a radioactive iodine dose will go preferentially to thyroid tissue. This is chemistry as targeting. Again, the key is that it is controlled. Dose is chosen, patients are monitored. Instructions are given to limit exposure to others while the radioactivity decays, because the universe is indifferent, but hospitals can be meticulous. Even the simplest imaging reflects this discipline. A chest X-ray is fast and low dose compared to many other scans, but it is still not treated like a toy. The beam is collimated, shaped to the area of interest. Shielding may be used where appropriate. Repeat images are avoided unless necessary, because no one wants a story like the dial painters repeated in a different costume. Now, after all that, you might wonder what happened to radium itself. Did it vanish from the world? Not exactly. It simply lost its glamour. Radium is still radioactive, still chemically similar to calcium, still capable of harm, but it is no longer casually smeared onto consumer products. Glow-in-the-dark items now typically use safer photoluminescent materials. They absorb light and re-emit it slowly, like a battery that charges in sunlight. Strontium aluminate is a common modern phosphor. It glows after exposure to light without needing radioactive excitation. The glow fades because it is not being continuously powered by decay. It is powered by stored energy. So your child's glowing stars on the ceiling are not tiny radium bombs. They are just crystals that hold light briefly. It is a small victory, a swap, a better material for the same job. And it illustrates another comforting pattern. Science does not only discover dangers, science also invents replacements, not perfect ones. Nothing is perfect, but often less harmful ones. And the invention of replacements tends to happen only after you learn what the original material was really doing, which brings you back to the dial painters. Again, they were harmed during a phase when society knew enough to be curious, but not enough to be careful. That awkward adolescence of technology. We still live in that phase, in different areas, chemicals introduced faster than they are tested, new nanoparticles, new flame retardants, new solvents, new pharmaceuticals. The lesson is not that everything new is bad. The lesson is that novelty is a risk factor, not morally, statistically, because unknown properties cannot be managed. And what you cannot manage manages you. Now, let the scale widen gently, not to scare you with infinity, but to make the radium glow feel small. Because it is small, it is a little chemical lantern in a universe where energy leaks everywhere. Everything that glows is spending itself. Even if the spending is slow, a glow is a form of entropy in costume. Energy dispersing, order loosening, a gradient smoothing out. Stars shine because they are not at equilibrium. They are hot in the core, cooler at the surface, and they leak heat as light. A candle flame shines because fuel and oxygen are not yet evenly mixed. They react, releasing energy, and the products drift away. A firefly shines because chemicals are kept separate until an enzyme helps them react. A watch dial shines because radium is not stable, and zinc sulfide is willing to translate violence into green light. Glow is not a miracle. Glow is a process, and processes end. Some end in seconds, some end in millennia. Radium's half-life is long enough to feel like forever on a human scale. But on a cosmic scale, it is just a sigh. It is still decaying, still paying out energy, still moving down its decay chain, one transformation at a time. And each step produces daughters. Radon gas, polonium, lead, a slow family tree of atoms. Some daughters are more radioactive than the parent, some less, and some daughters are downright impatient, with half-lives so short you could miss them between heartbeats. Each step down the chain is a new personality of atom, with its own way of throwing energy away. You do not need to memorize the entire genealogy to understand the feeling of it. It is a slow argument with stability happening inside matter that looks perfectly calm. If you could hear radioactivity, it would not be a roar. It would be the faint, uneven ticking of countless tiny decisions. An atom waits. An atom changes. An atom becomes something else and tosses a particle into the dark. That is why the dial paint never needed recharging. It was plugged into time itself. And time is an infinite budget until it is your budget. Radium in those workshops was handled like a craft supply, but chemically it behaved like a long-term resident with no intention of moving out. Biologically, it behaved like calcium's unsettling cousin, and socially, it behaved like a rumor that takes years to become a headline. When you look back at it now, the tragedy feels obvious, but that is because hindsight is the safest form of intelligence. In the moment, the world did what it always does with new power. It used it first, then asked questions later. Sometimes it asked questions only after enough people got hurt to make ignoring it expensive. This is not unique to radium. It is the default setting of a species that learns by scraping its knees. The quiet part is how the science of radiation moved forward afterward, not just in labs, but in policies and workplace habits. The glow taught people to treat invisible forces like real forces. Not vibes, not superstition, not personal toughness. Real physics interacting with real tissue. And once that idea settled in, it spread. Because it had to. You could not build the 20th century without building a safety culture to survive it. Even now, when a modern radiation worker clips on a badge, it is a small memorial, a thin rectangle that says, "We will not do ignorance again, at least not in this particular way." The same pattern shows up in every hazard story that followed. A new material arrives, marketed as clean and efficient. Then, the boring work begins, measuring exposure and tracking disease. Then the arguments begin about proof and responsibility. Then finally, if you are lucky, the rules become normal. Normal enough that people forget why they exist. That forgetting is both comforting and dangerous. It means the rules worked, and it means you are tempted to stop caring. So you keep a small thread of memory, not panic, just awareness, because the world is full of ordinary objects that once had sharper edges, and some of those edges are still there, just sanded down by regulation and habit. Consider the simple idea of a threshold. People love thresholds because they sound like a clean line. Below this, safe. Above this, but biology does not always respect clean lines. For many carcinogens, risk behaves more like a dimmer switch than a light switch. Lower exposure usually means lower risk, but not always zero risk. That is why the phrase, "as low as reasonably possible," exists. It is not poetry. It is a weary compromise with uncertainty. Because you cannot run a world on zero risk. You can only decide what risk is worth the benefit. And who gets to choose? In the Radium dial shops, the workers did not truly get to choose. They were not given the information needed for consent. They were given a story instead. A glowing story, literally. And when science is used like a story, it becomes propaganda in a lab coat. That is another reason detection matters. Instruments do not care what the company brochure says. A Geiger counter clicks anyway. A film badge darkens anyway. Bone accumulates radium anyway. The body keeps records even if nobody wants the paperwork. And that is part of what makes the radium story feel so haunting. The harm was not dramatic at first. It was administrative. Small exposures, repeated, a workplace routine, turning into a biological ledger. The kind of danger that thrives in environments where nobody has time to ask why. Now let the scene change again. Gently. You are not in a workshop anymore. You are in a more modern kind of facility. The kind with polished floors and neutral lighting. The hazard is still invisible, but the attitude is different. There are signs on doors, not because signs stop radiation, but because signs stop humans. There are interlocks that prevent machines from running when doors are open. There are training sessions with slides that make you want to nap, and that is good. Boring training is often what keeps the interesting accidents away. In radiation work, so much safety comes down to habits that feel almost petty. Do not eat here. Do not drink here. Do not touch your face. Do not bring your gloves to the clean area. Do not take the pen from the hot lab into the office. It sounds like someone nagging you about crumbs, but contamination does not need a dramatic route. It loves the route of convenience. A smear on a glove, a fingerprint on a doorknob, a flake of dust on a sandwich. Congratulations, you have just turned lunch into an internal dose. So, the modern world separates spaces. Hot areas and clean areas, controlled zones and public zones. Not because the radiation is thinking, but because humans are. Humans are the ones who wander. Humans are the ones who forget. So you build systems that assume forgetfulness. And if that sounds cynical, it is. Cynicism is sometimes just realism with fewer decorations. Now, speaking of separating spaces, you can zoom out to the largest separation of all, the separation between you and the universe outside your walls. Because radiation is not just a human-made hazard, it is built into the planet, and it falls from the sky. Cosmic rays strike the upper atmosphere and produce showers of secondary particles. You do not feel them. You are not supposed to. But your body, quietly, is always handling small amounts of background damage. Cells repair DNA breaks that happen naturally, from metabolism and from radiation and from sheer chemical chaos. Life evolved in a radioactive world, and it adapted. Not perfectly, just enough. But enough is a strange word, because enough changes with dose. A little background is a whisper. A concentrated source in bone is a constant shout. So when people ask, is radiation always deadly? The honest answer is gentle and annoying. It depends. It depends on the kind. It depends on the route. It depends on the tissue. It depends on time. Science often answers questions by refusing to simplify them too much. That refusal is not meant to be cruel. It is meant to keep you alive. Now, while you are here in this wider view, it is worth noticing something else. Radiation is one of the few hazards that comes with an unusually dramatic reputation. People fear it in a special way, partly because it is invisible, partly because it is tied, culturally, to bombs and disasters. But the radium dial story is a reminder that the scariest exposures are often the quietest ones. Not the flash, not the siren, the routine. And the routine is exactly what modern safety tries to interrupt, with measurement, with limits, with annoying rules. It is also why occupational health became a discipline, not just a moral impulse. You cannot rely on goodwill to beat profit margins. You need standards, inspections, enforcement, and boring documentation. Because the universe is indifferent, and companies can be indifference costly. That is not a fun thought, but it is a stabilizing one. It tells you why the world has guardrails, not because people are naturally careful, but because somebody wrote down the consequences. Now, slide back down to the scale of a human body again. When radiation hits tissue, it creates ion pairs, knocking electrons away and leaving charged atoms behind. Those charged fragments are reactive. In a watery body, much of the damage is indirect. Radiation hits water molecules, splitting them and creating free radicals. Free radicals are chemically restless fragments that want to react with whatever they touch. They can damage membranes, proteins, and DNA. So even though radiation is physical energy, the injury becomes chemical chaos. Your cells are not helpless in chemical chaos. They have antioxidants, repair enzymes, checkpoint systems. They pause division to fix damage. They trigger cell death when the damage is too much. That last part, cell death, sounds bad, but it is often protective. A cell that dies cleanly can prevent a cell that mutates dangerously. Apoptosis is programmed cell death, a controlled self-destruction. It is your body taking out the trash before it starts a fire. Cancer can be what happens when those controls fail, when damaged cells escape the usual endings. So, in radiation therapy, the goal is to overwhelm the tumor's ability to repair. In radiation safety, the goal is to keep normal tissue from being overwhelmed at all. Same physics, different intention. Intention does not change the photons. It changes how you aim them and how you account for them. That is the human part. Now, you can feel the story wanting to drift into the stars again. Glow, decay, time, the indifferent universe. But before you float too far, there is still one more human-scale detail worth holding. The radium dial painters did not just change radiation safety. They changed how society thinks about occupational disease. Before stories like theirs, it was easier to blame sickness on personal weakness, on constitution, on bad habits, on vague moral judgments. Afterward, it became harder to ignore that work can be a dose, that a job can be a chemical environment, that money can be earned in exchange for invisible damage. And that changed the ethical math of industry. Not enough to make it gentle, but enough to make it measurable. There is a dark comfort in measurability. It means a harm can be argued with, a mystery can be investigated, a pattern can be made public, and the next time a miracle material shows up, someone might ask the boring questions sooner. What does it do in lungs? What does it do in blood? Does it persist in bone? Does it cross the placenta? Does it accumulate in food webs? Does it break down into something worse? These questions are not cynical. They are the price of being a soft animal with a clever brain. Now, speaking of clever brains, the mind loves to categorize hazards as natural or artificial, as if nature is innocent and industry is guilty. But radium is natural. Asbestos is natural. Mercury is natural. The danger is not that humans invented them. The danger is that humans concentrated them, moved them, milled them, aerosolized them, and introduced them to tissues that never asked for the meeting. Nature keeps many hazards locked in rock, diluted in soil, buried in ores. Humans are the ones who dig, refine, and distribute. You are a species that specializes in making rare things common. Sometimes that is beautiful. Sometimes it is a disaster with a product label. Now, let the scene soften into something quieter and more cosmic again, but still tethered to the outline you are walking through. Small, bright things, little glows, a painted dial, a detector's click, a hospital scan, a star. Everything that glows is paying, and everything that pays leaves a trail. In the radium case, the trail was literal. A body that could be detected after death because the bones had become a source. That idea tends to stick in the mind because it feels like haunting. But it is not haunting. It is bookkeeping. Atoms do not forget. They just decay when they decay. Now think about the much larger bookkeeping of the universe. A star shines because its core is a furnace of pressure, forcing nuclei together. Fusion turns mass into energy, and the energy leaks outward as light. But that light does not leave immediately. Inside a star like the sun, a photon can take an absurdly long time to reach the surface. It bounces, absorbed and re-emitted, scattered again and again. A drunken, patient journey through dense plasma. By the time that light finally escapes, the energy began its trip long before your species had language. So when sunlight warms your skin, you are being touched by ancient work. And the warmth feels gentle, but it is still a payment. A star losing energy slowly because it cannot keep it forever. The same is true for you in miniature. You eat chemical energy. You burn it with oxygen. You keep your body warm. You leak heat into your room all night. Your warmth is your tiny glow in infrared, and it is comfortable because the energy is low enough to be harmless, but it is still entropy doing what it does. You cannot be alive without being a heat leak. Life is organized decay, arranged temporarily into a person. That is not meant to be depressing. It is meant to be accurate, and accuracy can be oddly soothing. It means you do not have to moralize the universe. You do not have to pretend it is fair or unfair. It is simply consistent. Consistency is the closest thing to kindness physics offers. Now, since we are lingering in the cosmic view, you can notice how many things glow that are not radioactive. Phosphorescent paint that charges under light, then releases it slowly. Bioluminescent algae that flash when stirred, because chemistry is triggered by motion. auroras that ripple in polar skies because charged particles collide with atmospheric gases, neon signs where electricity excites atoms that release specific colors. In each case, the glow is a translation, energy entering a system, then leaving in a form your eyes can enjoy. The universe loves translations. It turns gravity into heat. It turns nuclear binding energy into sunlight. It turns chemical gradients into muscle movement. It turns your brain's electrical activity into thoughts you cannot hold. In that sense, the radium dial was just another translation machine. Radiation into light, a dangerous power made pretty. That is the most human part of it. We decorate danger. We put it in jewelry, in toys, in paint, in miracle cures. Then we act surprised when it behaves like danger. Now, gently, let your attention fall back to the smallest bright thing in the story. A watch dial glowing on a bedside table. It is easy to imagine why someone would want it. Night is inconvenient. You wake up. You want the time. You do not want to light a lamp. So you buy the glowing dial, a small luxury designed to be useful. And the deeper truth is that modern life is built out of small luxuries like that. A non-stick pan, a waterproof jacket, a stain-resistant carpet, a scented cleaner, a battery that fits in your pocket. Each one comes with chemistry. Each one comes with a manufacturing story. And most of the time, you do not have to think about it. That is the bargain. Convenience in exchange for ignorance. Science is what breaks that bargain slowly when the ignorance becomes costly. In the radium era, the ignorance was deadly. In other eras, it is chronic, subtle, distributed, still real. So the calm cosmic perspective is not that nothing matters. It is that everything is connected by mechanisms, and mechanisms do not care about your preferences. If you put radium in bone, bone gets irradiated. If you put lead in dust, children ingest it. If you put asbestos in ceiling tiles, renovations aerosolize fibers. If you put mercury in waterways, microbes do chemistry, and fish do accumulation. If you put carbon dioxide in the air, the planet holds heat differently. The universe is a machine with no morality and excellent follow-through. That is why scientific thinking is basically learning to predict consequences before you pay them, or at least before you pay all of them. Now, there is another kind of glow you carry with you that is worth mentioning because it ties the human scale to the cosmic scale. Your body contains potassium-40, a naturally radioactive isotope. It decays slowly, and it is part of why every human is faintly radioactive. Not enough to matter for health in normal conditions, just enough to be true. And carbon-14, formed in the atmosphere by cosmic rays, becomes part of living tissue through the food chain. That carbon-14 decays too, slowly. That decay is what makes radiocarbon dating possible. So the universe's background radiation becomes a tool for archaeology and geology. Once again, the theme returns. The same physics that can harm you can also inform you. It can tell you how old a bone is, how old a wooden beam is, how long since a plant stopped exchanging carbon with the air. Time becomes measurable because atoms keep clocks inside themselves. Radium was a clock that nobody asked to carry. Carbon-14 is a clock you carry politely, without consequence. Different isotopes, different energies, different risks, different usefulness. Details matter. They always matter. Now, if you listen closely to this whole collection of stories, you can hear a softer message under the hazards. Humans learn slowly, but they do learn. Not as individuals necessarily. Individually, we remain reckless primates with impressive tools. But culturally, over generations, knowledge accumulates. Radium dial painters suffered, and the next generation got stricter workplace standards. Children were poisoned by lead paint, and later generations banned it and built abatement protocols. Workers inhaled asbestos, and later generations built removal procedures and legal accountability. Mercury poisoned communities, and later generations wrote advisories and limits and disposal rules. This does not undo the harm. Nothing undoes the harm, but it changes what happens next. And changing what happens next is the only real power a species like yours has. Now, let the cosmic lens narrow again, not to end, but to stay grounded. Imagine your room, the one you are in right now, as a small, controlled environment. The walls are solid. The air is filtered at least a little by the fact that it is indoors. The objects around you are regulated versions of older ideas. Your smoke detector is a tiny piece of nuclear physics, quietly watching for fire. Some smoke detectors use americium, a radioactive source that ionizes air in a small chamber. When smoke enters, it changes the ionization current